go. So today's topic is about FIR filters. Let's go to the this theory part first. This is very practical theory actually, and kind of sort of makes sense. So first, why FIR filter? Or filters? Why filters? Okay, sorry, not my best day. Basically, the filter responses are divided into different classes based on the spectral response. So we have low pass, band pass, band stop, high pass, multiband filters, and then some special filters also for phase. But anyways, we are not focusing on those. But the digital filters especially are categorized in two types based on the impulse response. And those are the finite impulse response filters and infinite impulse response filters. FIR or IRR. Okay, about the spectral properties. Those are the, say, specifying parameters for any low-pass filter. So it has the cutoff frequency somewhere, and corresponding to that one, it basically defines the passband. Then it has the stop band, which is defined by actually 2 points. Or actually a point in frequency magnitude response graph. Stop band attenuation is based on the last point on this, when the basically passband stops, and where we still are having enough of stop band attenuation. So it's basically defined by that point here. Similarly to passband, it's defined by -3 dB point or some other point here. So there are always, on both of the, it's basically a corner that defines it for passband, and also corner that defines it on the stop band. So basically you should think of a filter response so that, okay, it's a box. You cannot have any response here or there. So whatever filter fits into these requirements is okay. But anyway, so it's passband, stop band, and then what is in between is a transition band. High pass, same way, but it is passband at the higher end of the free spectrum. But anyways, a similar box. Band pass, okay, it's basically a combination of low pass and high pass. You can think of it as cascaded low pass and high pass. So basically what is different here is that we have two stop bands with two different specifications. So this could be different. So the other stop band attenuation could be higher than the other one. But that depends on the application. And of course, those transition bandwidths can be different. So it has more than just two parameters that are setting these specifications. Band stop, similar to band pass, but opposite. So now we have one stop band, which means one stop band attenuation requirement, and then two transition bandwidths, two pass band bandwidths. Okay. Usually this passband is defined by the -3 dB point, except if we have ripple on passband, meaning the amplitude response fluctuates. We can allow some changes of the amplitude response on the passband. In that case, that ripple actually defines this corner frequency, cutoff frequency. So it's basically, if you have -2 dB ripple, then when you have the last point still having that -2 dB here is defining what is the cutoff frequency. Okay, now we go to the why on earth we would like to have any filters on FIR. Okay, all the analog filters are IIR filters. All the analog. So why since we are in digital domain, what could be the reason to use the FIR? Two reasons. Always stable, meaning that basically you cannot get oscillations out of FIR. That's a good thing sometimes, especially if you have a very complex system. Then FIR filter is could be the choice because if it's always stable. Another one, it's also possible to get linear phase response, meaning group delay is constant, meaning the time difference between different frequencies when they go through the system are zero. So there is no changes in time delay. Okay, two good reasons, and those are, I would say, the only reasons to use FIR. Since basically, usually it's also a so-called expensive filter, meaning it takes a lot of computing resources compared to same amplitude response on IIR. For example, audio filtering with FIR would be waste of computing bandwidth, because there the linear phase response is nothing. Stability, well, yeah, if you are afraid of making your own the feedback loops on software, then you probably should try first the FIR to be on the safe side. There are three methods mentioned, but basically the first one, that's only to start with. So that's very crude way of doing a say a model for an analog system. There's an example of that one. The windowing method is the one that we are using on the exercise because it's basically explains how the design flow goes. It gives you a little bit better understanding how this, for example, zeros and poles and the amplitude response go together, or what happens when you modulate signal or actually modulate a system. Then third one, basically it's optimized design methods. That's the way to go. And there is actually in MATLAB there are tools to do it. I will show you also the MATLAB tool, but if you can use the well, as long as the exercise goes, I would recommend using this windowing method and typing commands. Okay, good. So the first method, impulse response truncation. The problem here is only the truncation. Impulse response you can take, for example, taking any system. All right, any system which is analog system at this point. You can feed in a step function and you get step response. And you can then basically sample it. Take long enough sample so this stabilizes the output. Okay, so that would be the h of t, not h of t, that's the step response. what you then go to sample it, so you have a S of n times sample time, all right, and then times window. So you basically are cutting it by multiplying with time window. Okay, so basically what comes out, you can then take this one and, okay, this is a linear system, so basically delta response, which is our impulse response, is simply S of n minus S of n minus 1 times that one, of course. So measure the step response, sample the step response, use differentiator to get impulse response, compare the analog frequency response with the digitized system response. Okay, so the easiest system on the world, analog low pass filter. You are familiar with that one. Okay, so lab setup, yes, you can do that lab setup. And just run a step function, meaning square wave. And then you get output would be the step response, although even this picture also shows one problem of this setup is noise. There's something extra. You see the signal is going a little bit like that, all the step function signal and also that one. That's because of the crappy equipment I had. And, you know, physics just works that way. Yeah. But anyways, so that's what happens then. So that green line on the amplitude response is the optimal analog system amplitude response, and the digitized, meaning the Fourier transform of our differentiated step response. And that's the difference. It goes pretty well until, let's say, 1 kilohertz. Those are pretty close to each other, but then we hit the noise floor. And that noise floor is only about minus 25 dB, which basically more or less correlates with the, if you see the noise on this kind of picture, you definitely see it well also on this kind of picture. So basically minus 25 dB is about 1/20th of the signal size is noise. Yeah, about 1/20th of the signal size. Amplitude is noise level here. Yes, it actually fits pretty well on this picture. Okay, but anyways, it can be done, but it has some say bad sides, and that's because by default this method always fails, and the reason is the window function. You cannot wait for infinitely long time. We don't have enough of time to wait for the output to settle exactly on the right, on the final value. Okay. Although, well, you just wait enough, meaning that you are having enough of the, or fast enough the sampling rate. It can give you pretty good approximation. Okay. Always fails, but it's kind of straightforward way to start analyzing systems. Step response, sample it, differentiate it, and that's your impulse response. And, well, you have to multiply it with some constant window size, so basically it's FIR type of system. Okay, next step is the windowing method. This is already a usable method, and it's actually pretty good for learning how filters actually work. There we start with an ideal low-pass filter with the desired cutoff frequency, meaning that we are, let me take that picture. I will show you a big picture. Big picture. Low pass filter. Ideal, meaning you have cutoff frequency here. The unity gain, meaning the amplitude response in passband is 1. Very steep edge here, so it's basically a box, and then continues down here at 0. So this passes only these frequencies and nothing else. So it's a low pass filter. Remember also that in this analog domain, the frequency goes also negative, just like in digital systems. So you also have the negative frequencies. So minus FC. There. That's an ideal low-pass filter, given a desired cutoff frequency. Then we use inverse Laplace transform. No, we are not actually using. This is the only time you will see the inverse Laplace transform. Otherwise, I would see a lot of students walking out. Oh, baby, it's not your favorite math topic. But anyway, it's useful tool. Okay, if you take the inverse Laplace transform of that one, you will actually get what? You will get impulse response. Okay, impulse response, meaning you're transferring that one into time space. So this is the frequency and this is time. On time space, that actually inverse Laplace transform. Laplace transform, that one. You will get sinc function, sine x over x. Continuous time still. So that's sinc. So it's sine of pi times x divided by pi times x. And I think you need to also, no, there's also some sort of scaling factor here, I think. No, it's not. Okay, yeah. Okay, good. So that is the inverse Laplace transform of this ideal low-pass filter. Gives you sinc, infinite impulse response actually. It's analog, starting from minus infinity and goes to plus infinity, not too usable unless you sample it. Okay. This should be symmetric, but on my drawing it's not. So it's basically next step is to take the sampled impulse response, which is this h of t n times. This is not the best. Do I have another? I can try. Okay, h of n equals that sampled sampled sync, and of course, to make it finite, you need a window. Oops. Window times that one. Mathematically, it's like this. Exactly. So you have window sync times, well, the sync, sampled sync times the window. Wow. Okay. If we take a look of the amplitude response of this system, meaning we take the take basically Fourier transform of h of n, or calculate the h of ej omega, amplitude response of that one. This box actually transforms into sync. So I will just draw a little bit of the, or do I have green? Green color, okay, I have green. Excellent. So that box actually transforms into sync. Okay, I can do it like that. But then the this sync, of course, transforms back into the box. So that's the same as that box here. And the multiplication in time space is actually the same as convolution in frequency space. Meaning that the final discrete time system finite impulse response of the system, let's put here the sample rate over 2, looks somewhat like this. It basically gets this passband cutoff frequency from the sync, and then it has the otherwise amplitude response characteristics of this box. So it looks more or less like that, and then of course the other side too. Okay. Anyhow, so we got control of cutoff frequency by using appropriate sync function. Good. Let's take a look at these again. So again, same thing but better pictures. So that's the continuous time low pass filter cutoff frequency, some f minus 3 dB point there, inverse Laplace transform that one. It gives you basically that kind of equation there. So it has some scaling factor on the beginning to f minus 3 dB divided by fs times sync n times that one. Yeah, sure. And then we are actually multiplying that one with a window. So here we have the sampled impulse response, finite impulse response here, sampled sync times that window. And yeah, convolution of frequency, multiplication in time, same thing. And basically that's what comes out. So we started with the ideal case of box type, so passes only the lower frequencies, not highest at all. Inverse Laplace transform, sample it, and multiply it with window to get it finite impulse response, and that's what you get. That's that you have a control of the cutoff frequency, but we also have the this anomaly, so the stop and attenuation is not perfect. not even close to perfect. And that's in magnitude, logarithmic scale. Okay, so the stop band attenuation is not even close to what it should be. So what you do, we can actually start smoothing these edges. So this part actually comes from the sharp edges of that box. So if we smooth the edges of that window, we'll reduce the amount of higher spectral components on our filter stop band, meaning that this one goes down, but at the same time transition bandwidth goes higher because it has more power distributed on lower frequencies. So instead of that sink, we would have a power density of something like this for that window, smoother window, more weight on the lower frequencies, but then smaller portion of the higher frequencies. And that takes the stop band attenuation down. Okay, different windows. Those are basically classical windows. The box is the blue one in here. Then we have the next window shape would be the Bartlett, which is just triangle. And even with this triangle, you already got something like minus 5 dB better stop band attenuation. But on the other hand, you are also then the filter is not that deep anymore. It's not responding that fast. So the stop band attenuation basically starts. Stop band starts later on higher frequencies. Then there are 3 other windows mentioned here: Hanning, Hamming, Blackman, and then there are some others. And basically, with the Blackman, that's my favorite from these. You get this purple line here, and okay, minus 72 dB minimum attenuation on passband. That's pretty good. But on the other hand, when you get smoother and smoother window, you get transition bandwidth higher. But we have now control of the stop band attenuation. So the sink actually is defining the cutoff frequency. The stop band attenuation is defined by the window shape. The third parameter would be, well, the shapes don't change much, but what we can do is to multiply the time. Multiplying of time is dividing of frequency. Time multiplication here means that we will start expanding the window, take more samples, get a longer filter. So basically the transition bandwidth depends on the number of points in our filter. And now we have everything what we need to design a low pass filter. Cutoff frequency. That was the sink. Stop band attenuation. Window shape. Transition bandwidth. That's the number of points. So all parameters that are needed in order to design a low pass filter. Okay. So yeah, adjusting the transition bandwidth is multiplying of time, division of frequency. Then how to make frequency transformations. Do I need this one? No, I don't need that one anymore. So have you taken the radio frequency or radio transmission basics 101 more or less? Yeah, you have it somewhere already. So have you heard of amplitude modulation? So if you have a signal spectrum like, well, let's make it like this, for example, an ideal case of signal spectrum, and you want to transfer that spectrum into some other place, symmetrical of course, with the information on a carrier, so you would actually have, if that is x of t, this would be x of t times cosine 2 pi fm times t. Right. So it transforms the signal spectrum on the around the new carrier frequency. Same thing in systems, linear systems, impulse response. The spectrum of impulse response is the amplitude spectrum of the system. If you modulate the impulse response with the carrier frequency, you are transferring that, transforming this low pass filter into band pass filter. So low pass with the half bandwidth of that FC would be then transformed into band pass filter. Exactly the same thing. With full bandwidth of 2 times FC. That was FC. Okay, easy. You just multiply it with the cosine, preferably cosine, since on sine you usually get a lot of zeros. This is a symmetrical impulse response. Oh wow, I already destroyed that part. Okay, yeah, I didn't need that. Okay, but anyways, so you start with the low pass filter design and then just modulate to have the band pass filter. So that's easy. Magnitude is scaled by half, so you need to basically do some scaling. Easy scaling. Low pass to high pass transformation is a special case of this one. If your modulation frequency is actually sample rate over 2, Nyquist frequency, then basically that's your high pass filter. You just swap the basically the real axis, meaning that basically you change the sign of every other term in C transform. Okay. Some details about this. The cut-off frequency of high-pass filter is basically, so FC of high-pass is the same as sample rate over 2 minus FC of the corresponding low-pass filter. Remember that one. So how the filters are actually defined. If it's defined by the special points, make sure that you have the correct bandwidth. And so there are some places you can make mistakes on the exercise, of course. So, okay. How about bandstop filter? Well, that's basically parallel, no, not parallel, the cascaded low pass and, no, cascaded, this is parallel, yes, low pass filter for the lower part of the frequency and then high pass filter for the rest. And you put those systems parallel, meaning you are actually filtering the low pass filter and high pass filter separately and then combine the signals, or you combine the system coefficients. On exercises we have that. One small detail, when you are paralleling systems, okay, parallel systems, then basically these stop bands are added together, meaning that the attenuation gets poorer. It can actually change up to 6 dB on the attenuation, on the stop band. Okay, good. So how to do the windowing method? You select first the minus 3 dB point of the low pass filter based on the design, what you are going to do, of course. Select window shape for stop band attenuation. So for different, it's application specific how much you need a stop band attenuation, enough to reduce the noise below usually the quantization noise level. That's enough. Then adjusting window width for transition bandwidth, and then basically, if needed, do some transformation. Pass band, band pass filter modulated with the center frequency of the pass band. High pass filter modulate with the minus 1 to the power of n, because the modulation frequency is actually cosine 2 pi fn divided by fs times n. So it's cosine n pi, meaning it's plus minus 1. Plus 1, minus 1, plus 1, minus 1. So, okay, band stop filter, design low pass and high pass filter, and add the filter coefficients. So it's the same as adding the systems, or putting those on parallel. You have had this in some course already. So if you have the cascaded systems H1 and H2, then this one actually is same as H1 times H2. So that's cascading. And then parallel systems H1 and H2. That's the parallel system. Then the overall transfer function is H1 plus H2. Okay. Wow. That was some theory. Let's go quickly through the windowing method. So the start point was the ideal low pass filter, inverse Laplace transforming it to continuous time impulse response, which is sampled and multiplied by a box, and the box transforms into the sink on the frequency space, meaning that you get this kind of the stop band attenuation is not ideal, but you can live with it by smoothing the window shape, smoothing window edges. So smooth window shape, some of them here, and some compression. And last, you adjust the transition bandwidth by multiplying the time, taking longer time sample. So that actually shows 4 different values of the window width. And we start from blue one, 11 points is 10th degree system. So green one is double of that one, so 21 points. Okay, meaning it's half of the transition bandwidth, and so on. Yeah, then if needed, do this transformation from low pass to any other frequency, basically based on the amplitude modulation. Okay, low pass to high pass is just a special case of the modulation. Then band stop is low pass plus high pass. Okay. Wow. That was something. Let's take a look at exercise. So the exercise, what I'm up to on my exercise. Final impulse response systems. And basically first question is about comparing the amplitude responses for different window shapes. Doing basically the same thing what I have done on my slides there. Then selecting a window and how wide window you need to take in order to change transition bandwidth by the factor of your secret number. Yes. Really? That's bad. Oh, yeah, you are right. There you go. Now you have access. Ooh, see. Oh boy, that is very popular for a reason. Okay, good. But anyway, so playing with the system. So first one was the finding a window that fits into the stop band attenuation criteria. Then select one of the previous windows, how wide window you need to in order to change transition bandwidth by factor of 0.SSS. Okay. And then design a low pass filter with the following properties. Okay. What else? Then transforming again. Yeah. So basically, there's plenty of things to do here. I'll start it now, but in 15 minutes, I need to take a break. But you can basically continue working on the exercise, and then I'll come back and tell you more. So, finite impulse response system. Let me go and start my Octave. Graphical user interface there. There we go. So, how to design a low pass filter? FIR low pass filter. Okay. First, I need to start from somewhere. So let me first get some values here, like sample rate equals 2000 Hertz. So this would be a system, data logger system or something like that. Sample rate. Okay. Then on this filter, what I would like to have next is, cutoff frequency. Let's make a low pass filter with the cutoff frequency with, say just for fun, 250 Hertz. And now we just need to make the region of interest and make the sink. So my target here is now to find out a FIR filter of some length with, say, first, I can see that the cutoff frequency actually can be controlled. Then we go and smooth the window and do the rest of the magic. Okay, so my window sink would be simply, okay, I do one more thing. Fn equals Fs over 2. So that's just for fun, Nyquist frequency. There. So impulse response at this point would be just the box times Fc divided by F n times sink of n times Ts, meaning the n would be, say, -10 to +10, symmetric, times Fc divided by F. Okay. That's the window sink. And then we just take a look at the frequency response. HH1. 1 is now the parameters for the feedback, and we have no feedback, only the first parameter, YFN. And then 1024 points and sample rate Fs. I think it went something like this, and yes, wow. It's nice to show a demonstration that works. So basically, this is a low-pass filter by itself, which has 250 Hertz cutoff rate, somewhere in here, -3 dB point, about 250. And the stop band attenuation, actually the stop band starts around 300 Hertz, but it's only about 20 dB. Not too much. Okay. But we got the cutoff frequency fixed. Next step, the what is the stop band attenuation? With different window. Let's check what kind of windows we have. Do I have to load the okay, signal? Yeah. If you are using Octave, you may need to do this, but on MATLAB you don't need to. Let's load control. There we go. Okay, so we have some signals, but I didn't see help window. Does it say? No, let's see. Does it say anywhere what kind of windows it has? Okay, now we can find some windows here. That was the Blackman, Bartlett is here, and so let's see. I will take the help, for example, that Blackman, and there's supposed to be also some hints of where to find. But anyways, if you're using Octave, take a look at the what kind of window shapes there are on the Octave function reference list. Okay, for MATLAB, I think you get help window. It gives you also the window types that can be used there. Okay, so I will start with the Blackman, and then basically let's make the window is Blackman, and basically it just needs the one single scalar as an argument, which tells you how many points, and this must be the same amount as you have the window width, meaning the length of my HH. And we transpose this one. For historic reasons, these window functions have always been single row vectors or single column vectors, but the system coefficients are row vectors. So basically we need to just make the dimensions to match. There we go. So remember transpose. I'll just, should I put it? Transpose needed. And let's take new figure and see what happened for the frequency response if we take HH dot times WW. So this is the windowed sink. So that's what happens. Maybe I should actually zoom this a little bit. Zoom that one too, so to have them about on the same scale. Okay. So what happened to the stop band attenuation? Now we have about 70 decibels of stop band attenuation. Cutoff frequency is still the same, 250 hertz here. The transition bandwidth got haywire. So now it's basically the transition bandwidth was about 50 hertz before. Now it has a transition bandwidth is about 300 hertz. But we know how to deal with that one. We fix these, fix the width. So if transition bandwidth is now 300 hertz, but should be, say, 100 hertz, then we need to have wider wider window. Okay, and that will be, say, 3 times wider to cut it by the factor of 3. So basically we need to calculate the HH from not 10 to minus 10 to 10, but minus 30 to 30. Okay, we need to fix the window again, and then now we should have the that transition bandwidth again, where it should be. There we go. Oop. Oh boy, this is so sensitive today. Okay, so wider window, smaller transition bandwidth. And the ratio is directly how much less or more you would like to have on that transition bandwidth. Okay, that more or less covers the low-pass filter design part of the exercise. Now I need to go to another place for half an hour, about half an hour, I would say. So I will come there here at 4:30 or so and continue with this modulation to get the bandpass filter, high-pass filter, bandstop filter. That's 3:30. Sorry. Yeah. Yeah, I'll be back in 3:30. No.